Gente, agradecer aí, muitíssimo aí a inscrição na disciplina. Estamos aqui com o professor Pet, Universidade da Concordia, no Canadá. O professor Pet tem uma grande experiência na parte científica, mais de 80 artigos científicos, fator H acima de 20, mais de 2.000 citações, professor Pet. Mas além desse lado científico, o professor Pet tem uma empresa e tem colaboração com empresas da área farmacêutica. Então, ele tem uma empresa, colabora também com Big Pharmas, com grandes empresas na área farmacêutica. E a gente estava conversando agora há pouco que exatamente mostrar o protagonismo do químico e da química, que podem ser homens e mulheres de negócio também. Além de serem cientistas, também homens e mulheres de negócio. Então, até pedi para o professor Pérez também, além da parte científica, trazer essa experiência que ele tem com relação a indústrias, empresas, o que o Canadá faz de diferente em termos de química para estar tão desenvolvido. Então, é uma grande honra ter o professor Pérez aqui conosco. It's a pleasure for Professor Pérez to be here with us. Please feel free. It's a honor for us. And I will say you have a great experience in the scientific part and the technical part. And I feel que deixou as coisas open. I could open my eyes to this potential. Thank you, Professor Pérez. Feel free for your questions. I think the first time hearing language is not the next one. Thank you very much, guys. Ok? Valeu. Espero que aproveitem o máximo isso daí. Tá? A internacionalização é extremamente importante para a carreira científica, ter colaboração e ter abrir a cabeça em possibilidades e potencial que o cálculo teórico, a parte experimental tem para dar. Ok? Bacana? Professor, thank you very much.
Thank you so much for the invitation to come here. It's a great honor to give this course for the first time in this course. So that's why I'm so here to refer to. So sorry if I'm in front of the screen. Just to give you a little bit of my background, I have another presentation which is giving you a little bit of my research background. In synthetic organic chemistry. I did an undergraduate project in synthetic organic chemistry. In Canada, we have this thing called a cooperative education program. So during my undergraduate degree, I would spend 4 months on campus studying and 4 months going to industry and working in different industries. And so during my undergraduate degree, I worked in polymers and analytical chemistry, quality control industry. I had many jobs in many different industries. And basically what I learned in all those industries is what I didn't want to do. And that's an important thing in life, right? It's one thing to learn what you want to do. You don't know what you don't want to do. I didn't want to do any of these chemistry areas, even though they're fantastic areas, interesting in a little way, but they just weren't for me. And then when I went to grad school, I fell in love with organic chemistry, so human molecules is what I was trained to do. I did that. I followed that Stockholm Fellowship at Ohio State University in the United States. I spent about a year and a half there. And afterwards, to industry, I was a drug discovery chemist, making small molecules for antiviral applications. That's drugs that treated hepatitis C. I spent very years there in industry. And after that, I went back to academia and took a professor position at Concordia University, where I've been for the last 16 years. So that's the general background of my career refreshing. It's a long career industry and academia. My research focus is in 3 general areas. Again, I'm going to more details for the presentation tomorrow, but I'm making molecules, including different applications. One is towards medicinal chemistry applications, so there's a discovery. We have a project where we're collaborating with biologists to the anti-cancer groups. We have another area in materials chemistry, collaborating with physicists and novel optoelectronic devices, basically conjugated polymeric materials. We make the small molecule versions of those polymers. And then the other projects, which is in green chemistry, that's the focus of what I'll close today. Give an overview of green chemistry, the background here, where we've come from, green chemistry, and where we're going to research focus. I have another connection to Brazil. My wife is Brazilian, so she was born and raised in Forgione, which is not too far from here. That's where she is right now. So that's my connection to this country. Two children, Brazilian. They all speak Portuguese. I do not speak Portuguese. I'm Portuguese. So I included a slide in Portuguese to try to give some context to the slide, but it is in English. But if you have any questions about anything I presented or anything else that you want us to talk about in terms of grad studies, your advice, anything that I could potentially mentor you on, either come see me after the lecture or get my contact information. I'll be happy to answer anything else. Another thing is that not only because of my wife, but to give my background, my wife, she has a PhD in biochemistry from USP, so educated in Brazil. So I have another advice for her because I think she's an outstanding scientist, but I also have had one master's student currently at a PhD student from Brazil, so we're very and our department has many other Brazilians for some reason from this. But we have some from regions of Brazil as well. And so I think that the one thing I want to impart to you is that all the Brazilians that I've come across as scientists have been exceptionally strong and competitive. They've come against us. We have a great education system that's trained great scientists that can be competitive everywhere in the world. So we shouldn't underestimate the capabilities and what the possibilities are for going forward. So I think that's something an important message. I think probably the most important take-home message from what you're going through these next few days. Okay, so that is the general background that we're going to talk about. So this is the green chemistry short course. It's based on this website that is called Beyond Denying. I think that they do an excellent job of providing resources for green chemistry to teach it at university and at lower levels as well. I also talk to the post all of my notes, so you will have to and you'll have access to these after. So if you're interested in that, sharing them since I actually just updated notes from Beyond Denying, so you can get the original notes there. You can have access to my sort of those notes. So what I would like to talk about today is to start to give an overview of green chemistry, what green chemistry is, how we think about the chemistry and how it's evolved over the last 25 years, which is really sort of been the starting point for this way that we think about chemistry as chemists from a perspective. I would say it's probably not a different perspective because economists have always been trying to do green chemistry, which is thought of it this way. I think this is a formal way and maybe a way for us to come and do it from the beginning of our careers as opposed to doing that sort of virtual activity, which is something which we have done previously. We've done in coordination from the center. So accidents, unintended consequences, and basically the case for green chemistry. So we're going to cover some chemical accidents, not to point fingers, but just to look at them as historical touch points where we can use them as analysis of how we can think about the chemistry was done then and how we can improve on that. And so what I want, one thing the take-home messages right now to make sure that we don't keep misconception that chemical is that, right? Because chemistry is something which is all around us, and it's not the definition of whether it's bad or good. I think in the greater society, chemicals have been associated now with something negative. And I think that's problematic, and I think as chemists, we have a responsibility to educate about what we do. But everything that we do has an unintended consequences, right? So a new material costs, there's resource costs, there's costs, water costs, disposal costs. So everything that we create has also unintended consequences, and those have to be weighed in the greater scheme of the benefits that they generate from doing. And so what we're thinking about here is not doing best chemistry, but we're trying to reimagine doing chemistry better. That's the muscle. So if we just, take a simple step out and just think about naming everything around us that's chemical, if we stopped and looked around, we would basically come to the conclusion that everything in this room is made out of chemicals. The water that we drink is a chemical, right? And water is something which we need as a solvent of life. So essentially, life on Earth couldn't exist with this crazy chemical, which has a tiny molecular weight of every 18 grams per mole, and yet it composes about 2/3 of the surface. Right? So these are just an indication of one example of chemicals that have hugely important in everyday life. There's nothing that exists without see without being chemical. And so, having said that, chemicals are based on their use can be either good or bad. And so, water we consider essentially safe, and it's something which is innocuous. However, if you drank 20 liters of water in 30 minutes, you would die, right? Because you would extract all of the minerals, the sodium, potassium channels of the biochemical processes. And so water is not inherently good or bad. It's very dependent on the situation, right? And so that is the case for every single chemical. And so when we say that DDT, we're going to talk about that later, is a biochemical, it's context, highly context dependent, right? And that's what we're doing. So this is what essentially some of the things that we've thought about historically in terms of chemicals is that we've seen, like, a natural chemical is considered a safe chemical, right? And that's just simply not true, because we know as chemists that the source of where a chemical comes from has no impact on its safety, right? So if you make water in the lab, or you take water from a river, and again, you have to make a few assumptions here. If you make water, saying that you make 100% pure H2O in the lab, that's the same molecule, right? So it's the same molecule, it has the exact same effect. So the source of the molecule has no effect on whether it's safe or not. And so that's why we have to really think about it really from the molecular structure. And that's why chemists provide the most value to understanding this. Synthetic is dangerous. Again, there's so many examples of molecules that are synthetically safe, and there's molecules that are synthetically lethal, right? But there's also natural molecules. There's snakes, venom, there's natural and unnatural. Right, so again, synthetic is not equated with it's context dependent. Chemicals equals contamination. So again, this is dependent on the type of chemical and what it's being contaminated with. So some chemicals are perfectly adequate being mixed with water, for example, but then there's other chemicals for example, table salt, sugar, you mix it in your water, it disposes down your drain, and you're not going to have any significant environmental impacts. There's other things that you're going to dispose of in your drain, medicines, for example, that could have negative impacts. So essentially what we need to think about is, as I said already, is that the chemical structure is the most important thing, not any framing that we're not here. Dose and exposure are highly important. So some chemicals at very low dose, like water, are safe. At very high dose, very dangerous. Persistence, this is another important aspect of understanding green chemistry, is that chemicals that persist or decompose over a time frame of days to months versus chemicals that decompose over the time frame of hundreds of years. Right? Those are going to have very different consequences in terms of safety and the life cycle of those chemicals. Right? So some chemicals, the ideal chemical is one that you produce, and you can produce it either naturally or synthetically, and then it does its job for the lifespan that it needs to do that job for, and then afterwards it can decompose that chemical back to its principal components. That lifespan cycle is ideal for the use of that chemical that you so what this course is going to be is essentially a chemistry course. We're going to talk about molecules, reactions, mechanisms, and their properties. It's also, we're going to talk about sustainability, environmental, social questions that come up through chemistry. And in the analysis course, we're going to try to think about the problems that can arise through chemical use and how to critically evaluate this. This sort of comes back to another point. First, just as a show of